Non è una di che è grande quando manda a
All right, good afternoon, everybody. Last class. You're all doing well. I finished half the exam already. I'll just tell you that I finished the multiple choice section. Work half the exam. It's 11 multiple choice questions. I'll write the other half tomorrow, and then I'll post it for you guys on Thursday. That's all I had to say about that. I'll have homework graded for you this week. I haven't started on it yet, but I will. Probably tomorrow. What I want to talk about today, I just want to close up shop about enzymes, and I don't really have a lot of concepts to introduce them today or ideas, but rather I want to understand why enzymes in particular are so damn effective at their job, or so than anything man-made. In fact, as I've said before, the best man-made catalysts are those that mimic enzymes and other types of biochemical processes. There's something very unique about the way that the body, living beings, do chemistry, and enzymes and proteins in general are key to that. And I want to understand thermodynamically why that is. So we'll focus on a couple of toy examples and look at a specific class of enzymes, and starting to rationalize thermodynamically why enzymes are so much better doing their job than doing the same reaction in your organic lab in a flask without an enzyme. Maybe you have a catalyst. Maybe it's some metal that you buy from Aldrich, or maybe you're using acid or base catalysis, which we'll talk about today. And why, in particular, enzymes are even better than that. So that's what I'm going to target today. So this lecture will show the weakness of my biochemistry, but hopefully not the weakness of my thermal. So bear with me. Not going to give you a lot of insight about biochemistry, but I can give you some insight about enzyme action and functionality. So at the end of the last class, I introduced this kind of last concept that we'll use to tackle this problem. It's called Hammond's postulate. It's just a qualitative idea about transition states. And the idea is that if you have a sequence of steps in a reaction that are consecutive, that the intermediate between them, so you have two steps and there's some energy change between them, the intermediate most closely resembles basically the transition state. That represents a small change in energy from either your starting or your final conditions. And so the idea is that transition state, depending on relative energy of the starting position, involves a minimum of reorganization. So if you have an exothermic process where the energy drops, that means is that the transition state, which is the highest energy, has to be most similar to the state of highest energy. So we have two molecules, R and P. R is higher in energy. That means by definition, the transition state has to look more similar to R than it does P. And that's also the case for an endothermic reaction. There, the highest energy state is P, so the transition state most looks like P. And then in systems that are at equilibrium, say for instance, the racemization of that ketoester in the last homework, that inversion process, there your reaction, your product and your reactant, the S and the R, the enantiomers of your starting material, they're the same energies. So delta G is 0 between them. And so the transition state is literally right in the middle. Right? It's the one of the R or the S, I can't remember, has a group pointing out in this direction. The other one has a group pointing in this direction. And the intermediate, the achiroenolate, is planar. It's cut right in the middle. What's the difference? Okay, so that kind of tells us something about regardless of the catalyst, it doesn't matter what catalyst we choose, it doesn't change the energies of the reactants and the products, right? The catalyst only affects the transition state, the intermediate. And so if we have some sense of the thermodynamics of a process that may be or may not be catalyzed, we know that energy difference, we can get a hint, an idea of what the transition state should look like. Why is that important for enzymes? Well, enzymes' only function is to as efficiently as possible through evolution, stabilize the transition state for this process as much as possible. So the active site of an enzyme is constructed through evolution to optimize through this idea, in the sense that if the enzyme catalyzes an endothermic process, the binding pocket and active site of the enzyme is going to look more like the products than the reactants, and vice versa for an exothermic process. For an exothermic process, the enzyme is going to, in some sense, bind more strongly to R and look more like R than it does P. Because what will happen is that, let's take this example of an exothermic process, and the enzyme wants to minimize this barrier as much as possible. Well, the idea to make this reaction as fast as possible is you need to get a lot of R into the enzyme and get it to react. Once it gets over that hump, it's not a problem to form P. That's not the hardest step. Right? Getting over the barrier is the hard part. So the catalyst is going to look a lot more like R. It's going to want to attract R as much as possible in and fit it in nice and snugly. It doesn't really care as much about what happens to P after the reaction, because at that point the reaction's over and it really wants P to leave. The binding pocket's going to look a lot reactant phase. And vice versa for the endothermic system. For the endothermic system, there's no problem bringing R in. It's at low energy. The hard part is stabilizing P. So it's going to look more like the products. And then, of course, in equilibrium, we can think of it as half and half. So again, there's a wide variety of reactions that occur in the body. Some are endothermic, some are exothermic. Right? They're the endothermic. It's really easy in some sense to think about what's endothermic and what's exothermic, kind of in a net sense. The things that generate energy for us are exothermic, right? Metabolism. Things that consume energy to perform these functions tend to be endothermic, things that consume energy. So I want to look at some examples today and think about this idea about why enzymes are really about focusing their energy, their structure, and their form and their function to optimize, from this perspective, the stability of the transition state as much as possible. So I want to look at a really, really simple example today, and then a slightly more complex one that I think is more biochemically relevant than my toy example. So here's a good example of a biochemical reaction that occurs in probably one of your bodies. If it hasn't this week, it has in the past. Some of you don't take this medicine. Maybe some of you do. But here's a medicine that I think maybe you guys you actually synthesized an orgo, I'm not sure. I did. But it's this methyl ester, this carboxylic acid with phenol. At neutral conditions, it's an ion. So typically this has a sodium counter ion. Right? This is aspirin, methyl salicylic acid, as it's called. So everyone and their mother takes this medicine at least once in their life. And the way that the body processes aspirin is very simple. It's actually a multi-step process, but we can kind of summarize it into one thing. But basically, once the aspirin has been whatever it interferes with and affects, eventually it's going to leave the body, and the body has to metabolize it, so that it can excrete it. And there's a key step to this process to convert the material into something that will go into your urine stream that your kidneys will process. And the key for something to process in your kidneys, right? Because it's a very hydrophilic region, right? You're always passing water through your kidneys. You want your metabolites, you want your stuff that you want to excrete out to be water soluble. And aspirin is somewhat water soluble, but you can make it a lot more water soluble with a very simple reaction, right? And so the way that this works in the metabolism of aspirin is there's an enzyme, which I don't know the name of, we'll make up a name of it in a second, but the idea is very simple. It takes enzyme and it hydrolyzes the ester. To get this carboxylic acid, like a phenol derivative, carboxylic acid phenol derivative. And this is extremely polar. This is excreted readily. This is very water soluble. Right, so let's think a little bit. And there's also a repeat, which is you also remove the ester, which gives you acetic acid. Aspirin's main output is this phenolic acid. I forget the name of it off the top of my head. Acetic acid, vinegar, which is a very, very common excretion out of your bloodstream. Okay, so let's think a little bit about if we were to go into the lab. We don't have a body, we don't have an enzyme to facilitate this. How would we get this reaction to go in organic chemistry class? And again, the trick is that we need to, right? We need to cut this acetic acid out. Right? We need to hydrolyze the ester. If you go back to Harvey's class, whoever you had for organic, remember carbonyl chemistry, that's Orgo 2, right? Orgo 2. You need acid to do this, right? So water is what we're going to do is this OH is going to attack here as a nucleophile and hydrolyze off the ester to replace it with an OH. So the way this is going to work, let me just go ahead and redraw this structure down at the bottom to have a mechanism. So this is the an Orgo lab. One of the nice things about this reaction is that it's actually rather readily able to hydrolyze in acidic conditions because the carboxylic acid on the other side of the molecule at the ortho position actually stabilizes the transition state. And I can kind of show you how that works. The idea is that you have a acidic water that comes in, right? So you're going to have an H3O plus. So we have some acid. Right, and so what's going to happen is this O is going to hydrogen bond. The oxygen on the carboxylate is going to hydrogen bond to the H on that. Right, and what that does is that polarizes the OH bond here to kind of push more electrons towards the O. Right, so it actually makes this O more nucleophilic. This is a nice Lewis acid-base combination here. We have an electron donor and electron acceptor. And so that polarizes this bond. It pushes electrons and stabilizes that O plus. And that allows that OH to become a nucleophile. It has some excess of electron density, which allows it to attack the C bond, the carbonyl. Sorry, this should be a C here. Right. So, right, and so what do we get after this addition? Well, we still have our benzene ring. Yes, I am. Thank you. I'm just going to jam it here. Is that okay? I'll fix it on the next drawing. So we have an O minus here, which is the carbonyl. We have the O from the water. That has 2 hydrogens on it. Sorry, it has, 2 oxygens on it. And then the third hydrogen is hydrogen bonded to the carboxylate. And I'll draw the hydrogen bonds here. And there's some bond here as well. All right, so let's look at this intermediate. You can think of it maybe as a transition state, doesn't matter, some high energy structure. somewhere in the middle. What do we have here? Well, we have some OH, like some acidic conjugate acid like behavior here. Right, so we have some sort of acid base stabilization here, right? And if you want to think about Bronsted-Lowry, you want to think about it as Lewis, whatever you like, it doesn't matter. Perfectly fine here with water. And then we have something very interesting here. We have a tetrahedral carbon. And you can imagine there might be some other acid in there where this O takes an H from another high water, right, to make OH. That's also something possible. But here's the interesting thing, right? We've made this concerted structure. Right? This it's this water stabilized intermediate that is intramolecular, right? And how does this close out? Right, we want to kick off an OH and we want to return the OH, right? So we're going to leave this here. This is going to kick off. And then we're going to return here. Huh? And the sp3 carbon intermediate at the ester leaves, and we're left with an OH or an O minus. Carboxylate. And actually, we have an OH there. I guess we could, let me write that H in green because I drew it in green last time. Do that O minus. We have another water, H3O plus left over. That's that H3O plus that leaves. And we have acetic acid carboxyl. Yeah, I can cancel that out. Okay, so very classic ester hydrolysis. The opposite of this is an ester condensation, a Fischer condensation, which is probably one of the first ester reactions you learned. Exactly the same thing, just backwards, right? Esters are, in particular, they're always at equilibrium, especially in acidic conditions with the hydroxyl, especially for something like this. So this, you can go in the lab and do this, all right? And then you can also go find the catalyst, the enzyme that does this for you in the body. There's lots of places that do this. This is what's called the enzymes are called hydrolases. I'll write that here. The enzyme equivalent is a hydrolase. Or sorry, not a hydrolase. It's not moving OH, it's moving a carboxyl group. So carboxylase. Carboxylase, right? It removes a COO group from a molecule. Right? There's lots of carboxylases in the body. They all have different, again, very interesting. They're all divergent in the sense that they act on different molecules, different steps, but they're convergent in the sense that their active sites, the carboxylase active sites are all very similar. They're all slightly different by a few residues, which just changes the delta G of different molecules that come in. They have different selectivities. And then you go ask the question, what's the ratio of the rates of this reaction? Right, so we have some rate Kr for this reaction, it's the total rate. And you look at Kcat, the catalytic rate in the enzyme divided by the rate of reaction. And we look at it at two different pKa's. Right, so one will look at pKa at 6.8, that's biological. And then we'll also look at it at acidic conditions. What do I have it? 3.7, right? Which is the that's the pKa of acetic acid. At 3.7, the catalyst is 100 times faster. That's a decent increase in speed. No one would complain about that. But let's think a little bit about 6.8. Here we're at biological conditions with around 7. It's neither acidic nor basic. But the thing that I said about this reaction is that it needs acid. You can kind of do this with a base as well, but this reaction is slowest where you neither have a base nor an acid at neutral conditions. Right? This aspirin is fairly stable in water, right? Otherwise, it would be kind of a useless molecule if you took water and drank a pill. It would hydrolyze immediately in your throat or your esophagus or your stomach, and you kind of lost the point, right? So you don't. So this is fairly stable at biochemical pH. Right? So you would imagine, okay, well, then that means the catalyst is probably slower too for the acidic conditions. And it turns out that when you go look at the data for this, that in fact the catalyst is 5,000 times faster. What turns out to happen is that in the lab, when you go into organic chemistry class, the rate, the way that it's drawn here with water, the rate of that reaction is very pH dependent. Right? It doesn't go at all at biological pH or barely at all. And then when you put it in acidic conditions, it goes pretty quickly. But what you find in the enzyme is that even at biological pH, catalyst is not only faster, it's just fast. It isn't slow. Right? It generates a fairly significant rate. In fact, depending on the height on the carboxylase, the rate of the catalyst at 6.8 is faster than the in situ reaction at 3.7. Right? So not only is it faster, it's faster even than the regular situation without the catalyst at acidic conditions. Right? So it's extremely effective. And so you would say, okay, that must mean it's not using acid-base chemistry. Right? It's obviously has nothing to do with protons and Bronsted-Lowry. But it's kind of hard to imagine how you would do this reaction where you kick an acetic acid off without getting an OH in here. Some water has to come in, right? There's only so many places you can get OH from in the body, and water is the best place. So the catalyst must be doing something special in this system that not only gets it better than acid, but negates the necessity to use an acid or a base. Very unique. And this is entirely consistent across many, many different, of course, all of our bodies, the vast majority of our bodies enzymes work at biological pH because there's very few places where we aren't at biological pH. The exceptions would be some of our excretions are basic or acidic. I won't go into any more detail than that. Some are basic, some are acidic. But by and large, internal fluids are all mostly at 6.8. Okay, so this, I'm not going to go too much more into depth into this reaction in particular. I just wanted to motivate our discussion. I want to look at a much better studied example that's a little more complicated, but allows us to take this idea of catalyst enzymes providing some catalytic abilities that acid can't give us at biological pH. Think about that idea. What can the enzyme provide our substrates to circumvent these problems? All right, so I want to look at a much more like violent reaction in the body. And a place where enzymes are constantly breaking down molecules, which is in the digestive tract. So the molecule I want to look at, or the enzyme I want to look at, are what are called the proteases. These are enzymes that cleave other proteins into pieces. The example I want to look at in particular is what's called chymotrypsin. Trypsin, S-O-N. Is it S-A-N? Sorry, S-A-N, I'm sorry. Trypsan. This is a enzyme . in pancreatic fluid stored in the duodenum, which is a part of the small intestine. And it has one job, and one job only. Cleave proteins in waste. Maybe not waste necessarily, but digestive material. At a specific position which is the amide bond let me get the exact name. I got it wrong last time. So I get the exact location. I screwed it up last time, and I just want to make sure I don't screw it up again. Oh yeah, amide bond between an amino acid and another with a large, bulky, hydrophobic substituent. Right, so it only cuts in between two amino acids and a protein where one of the amino acids has a large, like, aromatic compound, aromatic functional. So let me give you an example. So here's an example. Imagine that you just ate a big steak, something that has a lot of protein, and you've got this protein coming in. It's this long chain of amino acids. There's an amide bond. Maybe, for instance, you have an alanine that starts here. So the first amino acid in your chain is an alanine. So this is alanine. Alanine is an amino acid with methyl at its beta position. And then the following one has some bulky substituent. Right, so here's a good example of an amino acid that has a bulky substituent. This is what's called tyrosines. Okay. So you can imagine, then this goes on, right? You might have some other things in your protein. This. Right? So we've got that basic alanine, and the next to it, tyrosine. And what chymotrypsin does is it grabs onto the space right here between alanine and tyrosine, and cuts it right down the middle at the amide bond. Right, so the place where we're going to make a cut is on this green line right here. We cut this molecule into two. This is where the trypsin comes in. Right there. Okay, so what's going to happen is we're going to make this a carboxylic acid on the left side. We're going to append an OH, just like we did before. We're going to hydrolyze that amide, and we're going to have an amine on the other side, NH2. Okay. So our leaving group is an amine, or an amine, a primary amine, NH2, and then our other leaving group is a carboxylic acid. Okay, so this again requires us to hydrolyze a carboxylic group, a carbonyl, right, which requires an acid or a base in normal situations. Right, so this is, I'll just write that here, right? This requires acid-base catalysis to make something that looks like this. I'll just go ahead and draw them for you. So So there's our 1/2, and then we have H2 here. So really sloppy benzene, but forgive me. Right, something like that. I write down. Right. Requires acid-base catalysis. Right. So how the hell do we get this? How do we get acid-base catalysis in a environment where there is no acid or there's no base, or rather than there is no abundance of one over the other, I should say. pH 7, there's equal amounts of acid as there is base, right? So again, this thing will hydrolyze eventually. But I'll be honest with you, you put this in water at set pH 7, you just let it sit there. You have this dipeptide, you just let it sit there in water, it never reacts. And you can wait millions of years and it will never cleave. So it's extremely slow at pH 7. You could basically say it doesn't go at all. So how does the catalyst circumnavigate and get around that limitation that we have for acid base? All right, it's a very simple idea. The idea is that the protein itself provides stability. That we're going to create an environment where this molecule will go in and fit in like a glove. It'll fit in snugly like it's a glove. And there will be amino acids nearby that provide the functionality to stabilize the transition state. There's going to be a nucleophile, maybe a proton, maybe a lone pair, right? Some negative charge, some positive charge. They're going to be around and they're going to be located in the right places to optimally stabilize this molecule. Right? And this is what evolution does for us. Evolution says, right, the idea is that these things are designed, there's an objective that an enzyme is supposed to do, which is to cleave this as efficiently as possible with as little energy as possible. And over the generations and generations and generations of evolution, the system basically finds these optimal structures, these enzyme structures, that do this as best as it possibly can with the language that it has to speak chemistry, which are 20 amino acids, right? The body has 20 amino acids to work with. And it turns out that only 5 or 6 of them are all you need to do this. The rest of them are for supporting structures. Supporting, as we'll see. So let's look at the very simple way that this motif works. Really, really easy idea. Right, so I'm going to redraw my molecule. I'm going to draw it a slightly different way. I'm going to draw the alanine, the phenylalanine first. We'll get the right picture up. Yeah. So bear with me. So this is the rest of the protein here. And there is a phenylalanine here. There's my little phenylalanine ring here. And then our alanine here. So there's my dipeptide linkage. And what this is going to do is basically you've got this, imagine you have this long chain. It doesn't really matter how long it is, but proteins are fairly flexible. Amino peptides are fairly flexible. They're going to fold in, and this thing's going to get fit into this binding pocket. I'll show you a picture of it. And the binding pocket inside of the trypsin is built to fit this molecule exactly. So trypsins in particular, they have what's called, in particular, a special region of the enzyme that is designed. It's basically a cavity that's built to fit these aromatic cells. So there's this, what we call the binding pocket. So on the trypsin, there's this like kind of cylindrical region, which we call the S1 binding pocket. And inside of this binding pocket, there's a bunch of other amino acids pointing out that provide some sort of attractive interaction with the phenylalanine. So it's going to be some hydrophobic residues that are attached to this trypsin, hydrophobic functional groups that give you van der Waals interactions and pi-pi interactions and aromatic interactions, things that benzenes like that stabilize them, right? So there might be another tryptophan, there might be inside of here another phenylalanine, maybe, could be any number of things. Maybe there's a tryptophan, right? There's some other, maybe I won't draw it. You can imagine there's some rings in there, right? That provide some stability to the ring, to the system, right? That allow it to lock in there, right? So this is like a hydrophobic of the trypsin. And this is, of course, in green is the trypsin. Right. So that provides that a little bit of thermodynamic impetus for this molecule to come in and lock in. All right. So that kind of locks this molecule into place. Right? You've got some stability, a nice place for your benzene to set, your phenyl ring to set. But now you've got to do the damn reaction. It doesn't really matter if it sits there or not. There's always going to be attractions, but you need a kinetic motivator to get this to work, right? You need to start doing something now that you've attracted this peptide. So as we'll see, there are within the binding pocket, I'll show you a crystal structure of it afterwards. There's lots of different strands and different chains of the protein. It's all distributed around kind of in a crazy folded way. And there's other strands somewhere else in the protein that appear after many, many turns in the same region, right? It kind of bends and folds in on itself and then loops back around. You can imagine that this kind of goes like that. And then eventually what happens is that there is some band that crosses in front of the molecules of our protein. Maybe there's another band that crosses in front of it. So some other things, something like that. And these all, again, everything here contain amino acids, right? Proteins are just big, long, folded sequences of amino acids. So each step of this is some amino acid. And on these strands on the other side, when it comes to all proteases, effectively all proteases, the same three residues show up. The three active sites that the residues are the functional groups on the trypsin that provide the kinetic impetus to do this reaction, the actual mechanism. They're conserved amongst the entire class of peptides. You see this sequence of amino acids over and over and over again. And the three are in particular, we'll draw them. The first one is serine, which I'll call SER. Not everyone knows their abbreviations. A serine's functional group is a CH2OH. There's an OH group here. There's another one somewhere else on the protein, which is called histidine. Histidine is an aromatic molecule of two nitrogens. It's a 5-member ring, aromatic. There's a histidine, HIS. And then finally, there's another one, an aspartic acid, this ASP, which is like a acetic acid group. An O minus. Yeah. This is aspartic acid. Right. And chymotrypsin, they're not next to each other. All right. I've drawn it like they're next to each other, but the system folds so that they're close together, but they're not next to each other. In fact, if you label them starting from one end to the other, in chymotrypsin, this is amino acid 195. This is histidine 57, and this is aspartic acid 102. right? So they're on very different parts of this long sequence. Right, but the protein folds to get them in the right position. The reason why there's big gaps between these useful residues or amino acids in this protein is because you need those amino acids in between there in order for the structure to relax into a position that gets these into the right positions. The idea is that most of the amino acids in this protein don't matter, but they're essential, because without all the other scaffolding of the amino acids, these amino acids would never have the thermodynamic ability to get into the right position at the right time to facilitate the reaction. And so every amino acid is important, but only a few interact catalytically in the process. Very, very few. If you look at very, very complicated mechanisms of receptors and enzymes and other types of proteins in the body, when you look at the binding pockets, there typically is only 6 or 7, maybe less than 10 residues or amino acids that actually involve themselves actively in the process. They could be thousands of residues. So you think about these really, really large proteins that exist in the cell membrane to allow things to move in and out of the cell. Though some of the things like the proton pump that brings H pluses in and out, or sodium ions to maintain sodium concentration, gradients and things like that. Those typically only have 5, 10 amino acids doing the job. The rest of it is there just to control the structure and in some sense the motion of the protein as it accepts something and releases it. It's just all there as scaffolding. These 3 in particular do all the work for us, and the biochemists give it a special name. These are what are called the catalytic triad. See them all over. It's a sign of convergent evolution in the body, in that we have all these proteins that all react with different molecules. They all do different things, but they all use the same key tools to facilitate that. In some sense, the difference between different trypsins, different proteases isn't the mechanism that it performs, but rather the shape that it needs to make in order to fit the right molecule. It's all about fitting the right thing. Really important thing that biochemists like to say is that form is equal to function. The form of a protein determines how it reacts. And so if you have a big class of reactions, like a big class of proteins that all do the same reaction on different things, they all will have very, very similar properties, very similar motifs. But the rest of it will be different because they have to fit a different structure in, a different form. The function's the same, but the form is different. A little contradictory to what I just wrote there, but I think you get the idea. Right, so how does this facilitate this reaction? Right, remember we needed to do an acid-base reaction in a system with no acids and no bases. Well, again, one of the things that you learn in biochemistry is that and maybe you already know this, but at biological conditions, some of the acids and some of the amino acids aren't in their fully protonated form. Some of them are zwitter ionic, meaning they have a negative site and a positive site, so they're ionized. And aspartic acid in particular at pKa6 is in the carboxylate form. Okay, so that there's an O minus there always. It isn't an OH at pH 7. Right? So the nice thing is now we have some charge distribution. We don't have acids and bases, but we've got negatives and positives. And this catalytic triad facilitates this hydrolysis process working constructively together. So I'll draw in different color. The idea is that this O here is going to pluck the H on the NH on the histidine. This is a positive charge here, sorry, positive charge here. Right? Those electrons are going to push to the N. Right? So what we're going to do, we're pushing electrons to this nitrogen. We're doing an acid-base reaction. This is a Lewis acid reaction here, or Bronsted-Lowry. Those electrons are being pushed from this positive charge on this NH to this one over here. through the height from the aromatic system, right? That increases the negative charge on this nitrogen, making it more basic. And that nitrogen is going to attack the serine. So this attacks here. And what have we done? We've pushed that negative charge over to the serine oxygen. Now this oxygen is strongly polarized negatively. Pushed electrons towards it. We're pulling that hydrogen away. We're now making that serine nucleophilic. And so finally, what will happen is the serine will attack. So I'll step this kind of in order. 1, 2, 3, and 4. Right? And so by just transferring protons or electrons across this chain of amino acids, we can take a system that is nucleophilic but not protic, nor is this O particularly very nucleophilic. It's not nucleophilic at all. It's basic. If anything, this is an electrophile, not a nucleophile, but there's some negative charge here, and it will happily accept the hydrogen. Here's a free hydrogen for us. That's going to give us free electrons over here. Well, there's another free hydrogen and an oxygen to accept those electrons. Now that oxygen, OH, is a great nucleophile. This is a great nucleophile. And so that will attack and begin the process of cleaving our system. Okay, so now what does the intermediate look like? And it's going to be a little messy. But if we think about this reaction, what we have now, I'm just going to kind of roughly draw it. Bless you. Let's draw pH here. So now on the oxygen side, let me draw white again. I'm sorry. And then we have NH here. We have O minus. That's from the carbonyl. And then we have this kind of ether-like linkage into the serine. And then on the histidine side, we'll just kind of connect it like this. We'll draw the histidine in a different color. No hydrogen there anymore. Right, but there's now an H here. We've taken it from the oxygen on the carbonyl. And then we have down the line in the spark acid that is now protonated. And of course, this thing is nicely contained in its little shell. Okay, so we have this intermediate here, right? And so how do we hydrolyze this? Oh, sorry, that's not right. Yeah, that is right. Sorry, that is right. Well, we could do the same process, but backwards now. We want to kick off this NH, right? So we're going to cleave here. We're going to kick here. Right, this ammonia here is going to have that N is going to have a lot of extra a lot of negative charge from this pooling it. So it's going to take this hydrogen here, which is going to push the electrons in this direction. Right, and what we're left with now finally is our tyrosine. NH2. I've missed the OH. Oh yeah. missed the OH, right? And after a few steps, I've missed a step. I'll just write a few steps so we don't waste time. We just have one more hydrolysis step. We're going to have, I've drawn it incorrectly. So, a few more steps. Right, so what have we done, right? We don't have pKa equals 7. We don't have low pH anymore, but we have all of the capabilities. We have everything that we need. We have a base. We have an acid. Right? Asp 102 is our acid, our Lewis acceptor, or acid. We have histidine 57. That's a base, right? That's a Lewis donor or a base. And then we have the serine 195 residue, which is a nucleophile. So what we've done, instead of using water for everything and hoping that water has the right amount of protons, the right amount of nucleophilicity that we need, instead we use 3 distinct amino acids that in a sequence that provide us the chemical ability for this system to react properly at pH 7. So we don't need the acid. The system provides the appropriate acid-based nucleophile we need to maximize the rate of forming this. The amino acids themselves, in particular, right? They provide the chemical power, right? Amino acids are our chemical machinery that are substitutes, or I don't know what you want to call them, but like loose chemicals, right? Loose reagents, like water. Things that are just floating around. Right. I want to show you in particular an important thing, that the energy balance here is very, very subtle. Because you would think, okay, well, if this system, this catalytic triad works for all proteases, right? It basically is more than willing to cleave any amide bond. There's really nothing in particular about what I've designed that makes it selective to just tyrosine and the thing next to it. Because every amino acid shares this amide bond linkage. They all have. So there has to be something about the protein in particular that says, hey, I only want this amino acid linkage and none of the other combinations of the 20 natural amino acids. They all have it. Why is it not all peptide bond? Right, so there's very, very subtle effects that build in selectivity. And I want to show you a really interesting picture. The key part, the thing that builds the selectivity into the proteases, is that binding pocket for the aromatic. It turns out that the amino acids that are within this binding pocket tell you which amino acid is going to come in and lock in. It's very specific to the pocket. So I found this just in a rant. I was just kind of Googling late at night, and I found this really, really, really interesting figure. The S1 binding pocket determines which pair gets selected. All right, so this is a picture from a textbook. And these are pictures of that S1 binding pocket between chymotrypsin, trypsin, and elastase. Right, 3 different proteases that are in your GI tract. Right, these are our proteases. And as you can see, these binding pockets are different by 1 or 2 amino acids only. In particular, elastase and trypsin have two distinct residues that chymotrypsin does not. Elastase has two valine. I don't know what val is. This is a valine. And this is aspartic acid. We've already looked at that. That's aspartic acid. But chymotrypsin has neither of these, right? So what are these? Well, valine is just an isopropyl group. So these are bulky hydrophobic residues. They don't have a lot of interactions. They're just big and steric. Right? These are sterically large hydrophobic. Groups. And of course, aspartic acid is very polar. Polar protic. It loves protons. Loves to give them and receive them. And chymotrypsin has neither of those things. And the important thing is that these small differences lead to an entire different selectivity of the group that comes into these pockets. So I'll repeat these labels. I don't expect you to know all the amino acid labels, but I'll draw them for you. These different ones. In fact, I don't remember all of them either. And so F. So let's look at the different classes of these, right? So chymotrypsin doesn't have these bulky steric groups that really fill space. It also doesn't have the polar protic, and it recognizes the largest class of amino acids. So F is, if I remember correctly, F is phenylalanine. Yeah, it's phenylalanine. We've already looked at that. That was my example. I think that's the example from before. Y is tyrosine, which also has a benzene ring. So it's the same thing as phenylalanine, but it has an OH group at the para position. 1, 2, 3. So tyrosine. W is tryptophan, which is a methyl group with a indole. Indole. And M is a methionine, which is 1, 2, 1, 2, 3, 3 S. So thiamine F2. All right, so let's other than the methionine, which is kind of a strange. Oh, sorry, that's not thiamine. It's called methionine. Let me just give it the proper name. You can see that the ones that the largely accept methionine is kind of an alternate example. I think because the S, I don't know exactly what happens with this one. But these three all have aromatic linkages, right? They all have a large aromatic system, right? So this is a large empty pocket to fit a large empty thing. So this has a large volume, right? It has a large empty volume, and what it fits are large empty spaces. I wouldn't really call them empty molecules, but you get the idea, right? You need a hot dog in a hallway. All right, what about the other two? All right, trypsin has this very protic polar binding pocket. So naturally, you would think that it binds to more polar materials. And in fact, it does. K, strangely enough, is lysine. That has a, let me see, 1, 2, 3, 4. 1, 2, 3, 4. And then an NH2, NH3 plus. Right, so it's got a really long protonated amine that's flopping around. That's why it locks into this trypsin. You can imagine that's a great hydrogen bond acceptor. Just kind of draw it for you. Got this negative charge here and this positive charge here. And this is the aspartic acid, right? So you can see how that connects nicely. You have a really, really nice hydrogen bond. It's negative charge and this positive hydrogen. And then R, very similar. This is arginine, which is 1, 2, 3, 4 NH2 plus NH2, right? Once again, you can see how this is very protic, very polar. Got a lot of hydrogens, positive charges. That wants to connect to that aspartic acid, right? These are just very, very natural hydrogen bonding. And then finally, we have A and S, right? So the elastase has these very hydrophobic, sterically hindered groups, right? So we want something hydrophobic and small to go in there. Right? And so they accept A and S. A is alanine. We've already drawn that. That's just a methyl group. Right? Just a methyl group on that. And S is serine, which is a small alcohol, which is slightly polar, but not very. Right? Slightly polar. Polar and small. And of course, CH3 is nonpolar and small. Right. So we can already, just by knowing what's in that binding pocket, we can already have a good sense of what's going to happen. Empty binding pockets fit big things. Right? Big hydrophobic residues. Right? We want something, or we want chonk. This is going to fit something chonky. This is going to fit something polar. And this is going to fit something small. Right? Because it's mostly filled up with large hydrocarbons. Right, this is what I mean by function and form, right? Structure defines function. There's a relationship between function and structure. In the sense that how the protein evolves, again, the chemistry is exactly the same in all of these cases. The only difference between this one, and this one is where do they cut? And the only thing that determines the cut is what can fit into the pocket. And so every one of these proteases are different in their pocket design, but the actual chemical mechanism is exactly the same. All the peptide does is just build an environment that maximizes the stability of the particular target it's focused on. Okay. I have one more comment. We still haven't answered an important question. This can explain why proteases work so well at neutropenia. They don't need acid. But why do they still work better even at high pH or low pH? Why do they still work better in acidic conditions? Why is it that no matter what we do, if we convince you of something that in the reaction in acidic conditions that we talked about at the beginning, this one, the aspirin, right? The water here is acting as a catalyst, right? And the water is recreated at the end. So the acid is acting as a catalyst here. Why is it that even in the conditions that make this water catalyst most effective, which is to set the pKa just right for this acetic acid group, so to optimize the thermodynamics, everything acid-base is happy. Why is it that still, even in those conditions, the protein still is better? It's a very subtle point. There shouldn't be, in some sense, there isn't really anything wrong with this. We know water is really good at doing this. It's the classic example of an acid-base. But still, the protein, even in its complications, is still 100-fold better, even in the right conditions, the optimal conditions for water. And the reason for that is very, very subtle. Let's think about what's different and what's the same between the enzyme and the non-enzyme version of this reaction. In some sense, imagine that the protein that does this process, okay, it may have a catalytic triad, it may not, But let's just pretend it brings in another water molecule, right? It uses water as an additional reactant in the active site, right? Maybe it needs just some solvent to stabilize the system, right? So in some sense, the enzyme, in this example, the enzyme and the non-enzymatic version of it are almost exactly the same. You have some space where this molecule is being hydrolyzed by a water. In one situation, you're in a protein, in a binding pocket, and the other one, you're just free in solution. Even in that situation, the enzyme is still faster at room temperature. Why is that? Why is it that when I recreate the environment as much as possible, the only thing that I do is I just bring this enzyme in, just a new environment for this to exist in, it's still faster than just the water by itself? And it turns out the answer to this question is entropic. It's an entropy question. There is a special compensation in entropy that we have to deal with in both cases, but the protein gives us an advantage. The entropy question. Now, what do I mean by that? Well, let's think about how the entropy changes in this mechanism. Right? Remember, the entropy scales as effectively as the number of molecules and the temperature, the volume, whatever you want. Entropy goes up as moles go up. Entropy goes down as moles go down. So what do we have here? Well, we have effectively a reaction involving two molecules, right? A water solvent molecule and our aspirin. Okay. How does the entropy change as this reaction continues? Well, the entropy decreases here in the intermediate. And the reason why the entropy decreases is because now I don't have two freely moving molecules in the aspirin and the water are separate from each other on the left. They can move freely, mix freely. And now what I've done is I've locked them all into place. Everything is locked together. Now it functions effectively as one system. These now have to move together. So that reduces the entropy. So the transition state here is ordering. The entropy decreases. But as you can see, the entropy increases again afterwards because what I end up doing is I cut my molecule in half. So I've gone from one molecule to two. So the entropy is now up again. Right? So what has to happen for this reaction to take place is that the entropy has to decrease, the ordering has to increase before the entropy increases again. Right? So we have to go through an ordering stage before we go to a disordered stage. That costs energy. Let's see if we can understand why that is. Let's think about this on our reaction coordinate diagram. And here I put aspirin. And then we'll put our finalized material, which is our phenolic material. Whatever the phenol is, plus CH3COOH. We have to cleave this bond. It's probably going to be endothermic. We have to break a bond. We form new bonds. It doesn't really matter which direction. Okay, they may be endothermic, maybe exothermic. Doesn't matter. Right, and let's think about delta G of this reaction as a function of the coordinate. And let's remember that delta G is delta H minus T delta S. Okay, so when delta S is negative, becomes negative, delta G goes up, right? Delta G goes up. As it increasingly becomes negative, and as delta S is greater than 0, delta G will decrease. And so this is disordering, and this is ordering. Okay. And let's remember that delta S measures a mixture of things. It's just all the different motions the system can take. The more restricted the system is, the lower the entropy. Delta H measures things about bond strengths and stability. interactions, right? And stabilizing interactions lower delta H and destabilizing interactions raise delta H. So attractions make delta H negative and repulsions make delta H positive. And delta G goes down as enthalpy goes down and delta G goes up as enthalpy goes up. Okay. So let's think about this process in terms of H and G in our two cases for our catalyst, our enzyme, and without the enzyme, with an acid. All right, so let's I'll draw two different pathways, okay? And we're going to look at how H changes and how S changes through the system. Okay, so we know that the intermediate is some hydrogen bonded complex of the molecule with the water. So this is going to be aspirin plus H3O plus, and there's an H3O plus here as well. Right, as we saw that aspirin and H3O plus is more than happy to combine together. And so the enthalpy of this system may decrease. So we'll call enthalpy, this will be orange, and entropy will be red. We'll do blue. So what will happen is that as the system binds, right, the entropy, so as water binds to aspirin, step one, delta H will decrease due to hydrogen bonds, but we also have to break some bonds. Right, we have to cut things. We have to break a double bond. We have to make that tetrahedral intermediate due to bond break. Right, this is large, and the intermediate, the interactions due to the intermolecular interactions, they're moderate, right? They're moderately negative. And so the net positive, right, is that delta H increases to the intermediate, right? So we would expect there's a small decrease in energy due to the hydrogen bonds, but there's a big increase in energy due to bond breaking. And so the net energy is the sum of those two. I've written that in orange. So the net will be something like this. Right, so this is the net delta H at the transition state. And eventually the energy will decrease here. Right, well, what about the entropy? Well, we just saw that the entropy, right, you have to put everything together. You go from, with delta S here, delta S decreases because we go from aspirin plus H2O to aspirin bonded to H2O. Right? So delta S increases, which means delta G increases. And at the end, delta S increases at the end. So delta S decreases at first as we make, and then is at a minimum at the transition state. And then it increases again as we make more molecules. Right now we have 3 molecules. This is the entropy. Okay, so once we add H minus TS, the Gibbs energy of the system, which I'll write in green, we have something that's in between, right? We have something that's negative at delta S, which means that it adds to delta G. So the delta G of this reaction is much higher than the delta H. Right, so we get a large barrier. This is for the system. What happens? I'm running out of time, so let me just finish this. maybe it's obvious what happens now. Now, what happens when we put it in the enzyme? We still have to constrain a water molecule. So the entropy in the protein case also decreases. You also still get the hydrogen bonding interaction here. But what else do you get? You get more interactions. You get the binding pocket interaction, you get the catalytic triad interaction, you get the hydrogen bond to the water. So in the protein, you still have the same loss of entropy. The same loss of entropy in the protein. Right? In the protein, it still goes down. So in the enzyme, the entropy still goes down because you have to combine everything in the little space, right, in the little binding pocket. But now what happens is, and the bond breaking still is large, but what now happens is you have way more interactions. So the enthalpy of the protein interaction is much lower. So the enzyme interactions are much lower. And so when you add them together, that'll be the protein one, you get a less positive transition state energy. This is the G of the protein. So what happens is that in both cases, you have an entropy working against you. But the thing is that proteins provide a factor of 2, 3, 4 more enthalpically favorable interactions to stable. Therefore, you can never beat the protein. The protein always has more stability, more interactions, more things to bring things together and to keep things organized more than anything in solution will ever do. Okay, right on time. Thank you all for a lovely semester. If you need any help or any questions over the next week, just send me an email. I will have my office hours tomorrow and Wednesday. Otherwise, thank you all. Good luck if I don't see you next semester. If I do, we'll have some fun next semester. I look forward to it. Have a good break.